Okay, so just another reminder that the Unit 1 exam is this week. So I've announced this a couple times already, just a reminder to not wait until the last minute to take the exam. I'd recommend planning to take it on or before tonight. That way, if anything does go wrong, if there's a power outage, anything like that, you have plenty of time to, either wait for that to resolve or, find another option. Um, the plan for today is to finish one last example in 5.1, and then to discuss some applications of systems of equations. And we might also cheat a little bit and introduce, just for your information, you don't have to use this, some of the algebraic techniques for solving systems of equations. So just to give you a little bit of insight into that, that is technically a Math 108 topic, but I think on one or maybe two of these problems, I'll just kind of show you alongside the graphical method what the algebraic method might look like. The quote of the day today is one that I actually just heard this past week. It's by mathematician Gottfried Leibniz. He lived in something like 1600s, 1700s, somewhere in that ballpark, same time as Isaac Newton. And he's kind of credited as being the co-founder of calculus along with Isaac Newton. And I think there's some nuance there, and some people like to argue some of the details, but more or less he's the co-founder of calculus. And I'm watching this lecture series on music and mathematics, and I have to admit there was even a lot more math involved in music than I even realized. So it's kind of fun to see that application. And the quote that came up in that lecture series is from Leibniz, where he said in a letter to another mathematician, Goldbach, he said in Latin, of course, because they all spoke Latin back then is kind of the lingua franca. He said, music is a secret exercise in arithmetic of the soul or of the mind, depending on how you translate that word, unaware of its act of counting. So I thought that was kind of an interesting thought. Music and math we tend to think of as almost like two opposite ends of the spectrum. There's kind of the very logical and rational side, and then there's the very artistic side, and really they have a lot more in common maybe than we might appreciate at first glance. Okay, so finishing up section 5.1, I think we left off with this exercise last time, and this will be the first thing today. So first thing today is an exercise with this example of Bob packing his lunch of grilled chicken and white rice and so on. And we introduced this problem at the beginning of section 5.1, but we didn't solve it. And now we're going to look to solve it. We want to figure out how many ounces of chicken and how many ounces of rice should Bob pack for his lunch in order to meet his calorie goal and his protein goal. And hopefully, ideally, this will be a reasonable amount of chicken and rice, like, not a negative number. I mean, there's nothing mathematically saying that for this system of equations, if we just think of C and R as some variables, maybe the intersection of these two lines is in the second, third, or fourth quadrant. Maybe one of or both of the variables is negative at that intersection. That could be the case, in which case that's not really a good solution to our problem. I can't tell Bob to eat -3 ounces of rice and 12 ounces of chicken or something. And hopefully it's also like, not, 1 ounce of rice and 12 ounces of chicken, which would just make kind of a funky meal. So we want to choose our combinations somewhat intelligently based on our knowledge of just general science and nutrition and so on. But let's see if we can solve for how much chicken and rice Bob would want to pack for his lunch in order to meet these constraints. So take maybe about 5 or 6 minutes. And this is a more involved problem. You're going to want to solve, you're going to want to make one of these variables equivalent to y and the other one equivalent to x. And then solve both equations for y in terms of x, or for one of the variables in terms of the other. Then jump over to the calculator, plug those into the y equals screen. I guess we can clear this out. Plug those into the y equals screen. Pick a reasonable window, graph, and then try to guess a solution, maybe zoom in a little bit if you need to, and then verify your solution. So there's a lot to do here. So maybe something in the ballpark of maybe even 5 to 7 minutes. I'll kind of work it alongside you. And if we get to 5 or 6 and I feel like we could use another minute or so, then I'll make it closer to 7. So that's going to be the first thing on the schedule today. And then we'll just continue on with solving more examples, more applications of systems of equations. All right, so take 5 to 7 minutes, work through this one. In about a minute, I'll kind of start jotting down notes for you to follow along as usual. Okay, so I actually gave you a little closer to 8 minutes there. So let's take a look over the answers. Um, okay, so we're dealing with this system of equations. I chose to let C be x and R be y. And as I noted over here, if you did it the other way, if you associated R with x and C with y and then solve for y in terms of x, your intermediate steps here, your like blue and green equation, what you plug into the y equals menu will look a little bit different, but you should end up with the same answer at the end. Okay, so I rephrased my C and R equations in x and y, just so that way I have less to think about. I just rewrote them, being careful with all the decimal points and all of that. Just rewrote them so that I can now solve for y in terms of x in both of the equations. I do have to be really careful to do order of operations properly here. I want to make sure that I include these parentheses around, say, the 550 minus 67x or the 35 minus 5.3x, and just double check that I've typed everything in right, and it does look good. And I might as well start on a kind of minus 10 to 10 on both axes window, kind of our standard window to start on. I'm like hoping for an answer in the first quadrant, but it's possible that, that basically this choice of um, two components for my meal just doesn't get me the answer that I want. It's possible that the only way to get 550 calories and 35 grams of protein would be to have like negative chicken and positive rice or something, or right, that wouldn't be a physical solution, it wouldn't be a real solution, but that's what the mathematics would tell us is basically, well, you can't really make this work, so pick a different choice of foods or something like that, or adjust your expectations, one of the two. But we do see indeed it is looking like there's an intersection in the first quadrant, so that's a positive sign. And let's zoom in on the first quadrant. If we change our window to 0 to 10 on both axes, we still see that intersection. And it's a little easier to see here. It looks like it's about 6, 4 maybe. So then I'll zoom in around 6, 4. I'll take the x-axis from, say, 5 to 7, putting 6 right in the middle, and the y-axis from 3 to 5, putting 4 right in the middle. And when I graph that, I do see that my intersection is right in the middle, so I'm pretty confident about that 6, 4 is the answer. In a practical setting, this is probably good enough, right? If I have, and I really ought to state the conclusion here. So if x is 6 and y is 4, that means, well, x is associated with chicken. So 6 ounces of chicken and 4 ounces of rice will get the desired calories and protein. So from a practical standpoint, this is good enough. But if we're, answering this as a math problem, let's figure out if 6, 4 is actually a solution. It's certainly approximately a solution, but maybe the actual solution is like 6.03, 3.98. So let's plug 6, 4 into these two equations and see what we get. So I'll go to second quit over my calculator. And my first question is it true that 67 times 6 plus 37 times 4, if I do that, that does give me 550. So my first equation is satisfied exactly. And then let me check my second equation. Is it true that 5.3 times x or times 6 plus 0.8 times y times 4, does that give me 35? And it does give me exactly 35. So I have now verified this is a solution to the system up here. And nicely enough, it's kind of a reasonable solution. I mean, 6 ounces of chicken, 4 ounces of rice seems like something that is edible, right? It's not just like a whole bunch of chicken and a tiny bit of rice or something silly like that. All right, so let's look at some additional applications. So here's an example that's a little more abstract. So we have this setup here. We have the sum of two numbers is 12. One number is 7 less than the other. Find the numbers. So we know we're looking for two numbers. Let's give these numbers a name. Let's call them x and y. And their sum is 12. So that tells me x plus y equals 12. That's what the first sentence says. And then the second sentence says one number is 7 less than the other. So one of the variables equals, now 7 less than means that thing minus 7, right? Or somebody has $30 and I have $7 less than them, I have 7 less than 30, or 30 minus 7, $23. So one variable equals other variable minus 7. And it doesn't much matter which variable we pick on which side, as long as we're consistent. So I'll do something like y equals x minus 7. We want to solve for y in terms of x anyway to plug into the calculator. We might as well do this. Now, the second equation is good to go. It's already solved for y. The first equation, I need to subtract x from both sides. Y equals 12 minus x. Now let me solve this by graphing. I'll clear out these two that I entered for the last problem. And I need y equals 12 minus x as one of my lines, and y equals x minus 7 as the other line. And again, I'll set my window back to the negative 10 to 10 on both axes, kind of just standard window. We'll graph and we'll see what this looks like. Oh, and I get an answer that's kind of, it was almost off of the window, but we kind of barely made it on there. We see it's in the first quadrant. Let's zoom in there to get a little bit more detail, at least to make it easier for us to see the detail. And it almost looks like it's at like 9,3. But let me zoom in a little further. If we do window, let's say maybe from 8 to 10 on x, and maybe from like 2 to 4 on y. So here, let me screen cap this. Remember my order of operations here. I need to click off of the calculator, or the calculator will get all wonky when I try to screen cap it. All right, so what is my window here? On the x-axis, it's 8, 9, 10, and on the y-axis, it's 2, 3, 4. I was thinking like about 9,3 maybe. We actually see that 9,3 doesn't quite work. The first equation, 9 plus 3 is 12, actually does work, but the second one is 9 minus 7 equal 3. Well, no, 9 minus 7 is 2, so it doesn't quite work. Maybe like 9.5 comma 2.5 or something. We see that this intersection here is not going to be at a nice integer point that's going to be easy for us to guess. We can start guessing fractional values and so on, but that might get messy pretty quickly. So one thing we could do if we wanted to, we could do second trace to bring up the calculation menu, and we could search for an intersection using the calculator's tools. First curve, second curve, guess. And we do see 9.5 comma 2.5 actually is the solution. So is it true that 9.5 minus 7 is 2.5? That is true. And is it true that 9.5 plus 2.5 is 12? That is also true. So we verified that's the solution. But the point is that sometimes the kind of very manual method of find our intersection, kind of zoom in on a window until we can really pinpoint exactly where it is, sometimes that can be more difficult than other times. Here, I might have been able to kind of make this guess at this non-integer point, but you can imagine if this was like 9.37 comma 2 point, like 6.3 or something like that, that will be a bit more difficult. Okay, so for more challenging problems like this, we see that the graphical approach, let's just say, has some shortcomings, right? We're really using a visual method that's not super precise. Again, if we were just kind of looking at how to put a meal together, eh, if we're 5% off on our calories or our protein, we're probably not all of that concerned. It's probably close enough for us to be happy. But if we want a very precise answer, uh, it would be nice to have other solution methods, particularly algebraic solution methods, that don't rely on this kind of approximate nature of graphing and a visual interpretation. So we're just going to take a quick look at algebraic solution methods for this system. Try to select this and see if I can copy it down here. There we go. So this is a little bit of a diversion. As I mentioned, this isn't official material for our course. It's really Math 108. Depending on the curriculum, some folks cover it in kind of the Math 90 level course. Some folks cover it in the Math 108 level course. We opted for the latter. But I'll at least show it to you because it might ring some bells. It might, you might remember this, doing this from previous coursework. If you don't, that's perfectly fine. So one algebraic method is called substitution. And I did pull a bit of a fast one here because we actually kind of did this algebraic solution method earlier in our applications, and we really didn't say that that's what we were doing. But the idea of substitution is I solve one equation for one of the variables, like say this one here, y equals x minus 7. And then I say, well, if y and x minus 7 are the same thing, I can take my first equation, x plus y equals 12, but instead of writing y, I could choose to write x minus 7. So I could write x plus x minus 7 equals 12. And this just gives me a linear equation in one variable. Hey, I know how to solve these from chapter 2. I simplify. 2x minus 7 equals 12. I'm in standard form now. I get my variable terms together. That's already done. I isolate the variable term by adding 7 to both sides. And then I isolate the variable by dividing both sides by 2. Well, 18 over 2 is 9, plus another 1/2. X is 9.5. And then I get the other variable's value by plugging back in. Y equals x minus 7. But now I know that x has to be 9.5. Y equals 9.5 minus 7. Y has to be 2.5. And there's my solution. I might want to plug back in and check that x plus y equals 12, and it does. So that's the substitution method. Now, for a problem like this, right, that was pretty nice to do. It was pretty easy to do. One of my equations was already solved for one of the variables in terms of the other. That made it easier. And also, these weren't really terrible equations to solve. It would be much more challenging to do in a situation like this, where maybe I like, oh, maybe I solve my, oh, geez, there we go. Maybe I solve my blue equation for y in terms of x, and then I plug that into my second equation. Now I have 35 equals 5.3x plus 0.8 over 37 times parentheses 550 minus 67x. You can imagine that that's not going to be a super nice linear equation to solve. In theory, it works just fine. In practice, I'd probably rather use the graphing method here because, just these two equations aren't set up as nicely for an algebraic method as this one, for instance. And let's see if we can get 2 for 2 on the copying here. Perfect. Okay, there is another method, and it's called the addition method. The addition, or sometimes called the elimination method. And the idea here is if I have two equations, say A equals A and B equals B, I can add those together to get A plus B equals A plus B. Now, of course, usually my left and my right sides of an equation look a little bit different, but it's really fundamentally the same thing. So for my addition or elimination method, I want both equations in standard form, actually. So I want x plus y equals 12. Well, that looks good. And then I want to get my x on the left-hand side to get, say, negative x plus y equals negative 7 for my second equation. Now, similarly, if I just add these two equations together, if I have left side equals right side for the first equation, left side equals right side for the second equation. If I add the two left sides together, and then I add the two right sides together, that results in a valid new equation. So if I add the right sides together, 12 plus negative 7, or 12 minus 7 is 5. If I add x plus negative x, well, that's actually 0x, or that just goes away. And if I add plus y, I get 2y equals 5, or y equals 5 halves, y equals 2.5. And I could plug in to say y minus x equals negative 7 for y equals 2.5. If I add x to the other side, add 7 to both sides, I get x equals 9.5, as we expect. And just like with substitution, like this was a really nice problem to work with for substitution, and this one wouldn't have been nearly as nice. Same here. You can see that we had a heck of a lot of luck, so to speak, that these x's went away. If this, let's say, were, instead of a minus x, if it were a plus 2x or something, I'd have got like 3x plus 2y equals 5. Maybe that gives me another valid equation, but I'm not down to one equation and one variable. I can't really move forward very well with that. So there are some nuances here as well, right? I have to manipulate, in the general case, I have to manipulate one or both of my equations to end up with a situation where when I add them together, one of my variables goes away. So this worked out nicely in this case. That's, why I used this example. Worked out nicely in this case. We didn't really have to do much work, but the general case, there's a bit more strategizing that's involved. Manipulating one or both of the equations to get some cancellation to happen so that one of the variables goes away when we add them together. So we want to add the equations together in order to eliminate one of the variables That's why it's called the addition or elimination method. And I think that's really the reason that, uh, in my opinion, why this is more of a Math 108 topic. It really requires a lot of fluency and ability to work with equations, and really a lot of comfort with the operations so that you can appropriately strategize, right? It's hard to strategize when you're still working on the tactics, when you're still working on the, one line to the next, making sure everything is going well. So in my opinion, that's why it's more of a Math 108 topic. Okay. But again, the reason I showed these to you was just in case you've seen them in the past and you were, curious, why aren't we covering them? You know, kind of the answer is that substitution, we kind of already did a little bit actually, but addition elimination method requires, I think, a bit more strategy and a bit more comfort with working with linear equations. And part of Math 90, part of elementary algebra is getting comfortable working with equations. Okay, let's look at this next example. The Jones family took a 24-mile canoe ride down the Indian River in 3 hours. After lunch, the return trip back up the river took 6 hours. Find the rate in miles per hour of the canoe in still water and the rate of the current. So let's draw a little picture representing what's going on. So we have our water, and let's say that the current is flowing left to right. And the distance for this canoe ride from start to finish is 24 miles. And this took them 3 hours going left to right. And 6 hours going right to left against the current. What are we being asked to find? The rate in miles per hour of the canoe in still water and the rate of the current. So let's call the rate of the current C, and let's call the rate of the canoe in still water, and let's call that B for boat. So the speed of the boat, if the water wasn't moving, versus the speed of the current. Now, when the boat is moving in the same direction as the current its speed adds to the boat's speed. And when they're going in opposite directions, the current is subtracted from the boat's speed. Right? So when they're going to the right and the current's going to the right, the kind of apparent speed is the boat speed plus the current speed. And when they're going to the left, when they're traveling to the left, but the current's going to the right, their apparent speed is the boat speed minus the current speed. These would be the two speeds that somebody, say, walking along the shoreline would have to walk in order to keep up with the boat. When they're going left to right, the person on the shore has to walk really fast because they're rowing to the right and the current's pushing them to the right, so they get added together, those speeds. But when they're fighting against the current going to the left, the person on the shore can walk much more slowly, and because that current is getting taken away from the boat's speed. So this is two perspectives on the rate. The distance is 24 miles in both cases. And we know that distance equals rate times time, or rate equals distance over time. Okay, so going left to right, well, that took 3 hours to go 24 miles. So the distance over time is 24 over 3, and that has to be the rate of B plus C. And then going to the left, they went the same 24 miles. They came back the same way, return trip. It took 6 hours. This is everything's in miles per hour, 24 miles divided by 3 or 6 hours. And that is B minus C. And we actually see we get a system of equations for the speed of the boat and the speed of the current. We can solve these maybe for B in terms of C. 24 over 3 is 8. And 24 over 6 is 4. And maybe I'll let B equal Y. I'll let B be represented by Y in my calculator. So then I have 8 minus X for my first equation, and Y equals 4 plus X for my second equation. And again, I'll go back to my window, reset everything from minus 10 to 10. I'll graph. Okay, I see a solution in the first quadrant. Let me zoom in on it so I can see a little more clearly where I think that intersection might be. So here I'm 0 to 10 on both axes. And it looks like 2 comma, what is this? 1, 2, 3, 4, 5, 6. I think 2 comma 6. Or in other words, C equals 2, B equals 6. That looks like a solution. Does it actually work when I plug it in? Is it true that 6 equals 8 minus 2? That's true. And is it true that 6 equals 4 plus 2? That is also true. So these are the two speeds. The current is moving at 2 miles an hour, and the speed of the canoe in still water would be 6 miles per hour. Any questions on this one? Okay, one more example. So here we're looking at tickets for the community fair. Adult tickets cost $12. Child tickets cost $5. On the first day of the fair, 313 tickets were sold for a total of $2,181. How many adult and how many child tickets were sold? So maybe we know the total amount of money that we made, and maybe we were just using those little, rip-off tickets. And if you see that the person's a child, you charge them $5, and if you see they're adult, you charge them $12. So we know how many tickets we used, we know how much money we brought in, but we forgot to keep track of how many adults or how many children. So can we figure out how many adults and children there were? Okay, well, I know that, or well, first let's give names to these. Number of adult tickets, let's call A, and number of child tickets, let's call C. So I know that a total of 313 tickets were sold, so it has to be true that A plus C equals 313. And I know the total of money we made was $2,181. Each adult ticket sold for $12. So $12 per adult ticket times number of adult tickets gives us the number of dollars we brought in from adult tickets. So 12A. And similarly for the child tickets, 5C tells us the number of dollars we brought in from the child tickets. And if we add those two together, we should get the total number of dollars we made, 2,181. And now I'll pick one of these variables to solve for the other in both equations. So maybe I'll do C equals 313 minus A, and C equals 2181 minus 12A, getting my 5C term by itself and then dividing by 5 to get C by itself. If you want to do that in a couple of steps, that's perfectly fine. So again, let's go to our y equals menu, clear everything out. We have 313 minus, and here A will kind of correspond with X. And then my second equation, don't forget the parentheses, 2181 minus 12 times my variable A, which again corresponds with X here, and parentheses and divide by 5. Looks like everything went incorrectly. Now my window here, I might be tempted to just do the default, just follow the algorithm and not think about it, and do, say, minus 10 to 10 for my axes. But let's give this a little bit of thought. The number of adult tickets sold plus the number of child tickets sold is 300 or so, right? Or in other words, basically X plus Y is like 300. It's very unlikely that I'm going to see any intersection on, negative 10 to 10 on both axes, right? I'm going to need a much larger window. So maybe I'm going to start X, my number of adult tickets, at 0. Let's just start there. It is possible that the intersection is, in the second, third, or fourth quadrant. It's mathematically possible, but that would be kind of a silly example then, because we would have had to made an error in our assessment of how many tickets were sold or how much money we made. So the only way that we could really get a negative answer for A or C is if there's an error in the problem, or, in a practical sense, if there was an error in counting the number of tickets sold or the amount of money we made. So let's start both of these at 0, X and Y, or adult and child tickets. And let's maybe go up to, well, I know that if A is 0, C would be 313. And if C was 0, A would be 313. Maybe we'll go up to just like 350 or so, just to start with. It's probably a little too big of a window, but we should hopefully see the intersection here if all went well, right? This A plus C equals 313 is this first line, the one that where we see the y-intercept as well as the x-intercept. And that's all of the points, A comma C, that satisfy A plus C equals 313, where both are positive. So if we have an intersection that makes sense in the context of this problem, then it has to be somewhere along this line between these two intercepts. And I do indeed see that the other line comes in, this 12A plus 5C equals 2181, comes in and does give me an intersection here. It looks like it's on the left half of the screen and maybe on the top half. So let me, well, let me screen cap this. And remember, this is like 0 to 350 and 0 to 350. And I think, this would be about, say, 175-ish, something like that. And same here. So maybe I'll set my window in the X direction, maybe from 0 to, I don't know, I think maybe 150 should do it. Let's see. That might be a little too aggressive, but we'll see. And on my y-axis, maybe I'll go from something like 200 to 350. Again, it might be a little bit aggressive, but Let's see if we can get away with that. Okay, we did just barely make it in the window, so that's good. Screen cap this. And what was my window? On X, it was 0 to 150, and on Y, it was 200 to 350. And if I look at, kind of the midpoint between 0 and 150, it looks like we're to the right and to the bottom of the 200 to 350. So maybe I'll go from, say, 75 to 150 on the x-axis. I think that should keep my point of intersection in the window. And maybe I'll go from, I don't know, maybe is 200 to 250 too aggressive? I don't think it will be. So maybe I'll go from 200 to 250 on my y-axis. Again, if I get a little too aggressive, I can just back off a little bit. Right? And I can keep doing this. So I have 75 to 150 and 200 to 250. I can keep kind of doing this like bisection method, we might call it, until I get down to my answer. So I might do like 75 to 100 on X. That seems like that should keep the intersection in the window from the left to right from the horizontal direction. And we're going from 200 to 250 here, and it looks like it's about in the middle. So let's maybe try like 220 to 230. And again, if we miss it, we can expand our window a little bit if we need to. And it's still right in the middle there. So we're now at 75 to 100 on X and 220 to 230 on Y. So we're cutting down pretty quickly here. This kind of bisection method actually zeroes in on the solution pretty quickly. Right? I mean, just think we started with 0 to 350 on both axes, and we're down to 10 units vertically and 25 horizontally. Again, it looks like we're about in the middle horizontally. So about in the middle between 75 and 100, maybe something in the ballpark of like maybe 85 to 90. Let's try that. I actually do not remember what the solution is here, so I'm not cheating, I promise. So let's try 85 for the X-min and then 90 for the X-max. Again, we might get a little too aggressive. We might cut the window a little too much and the intersection be out of the window. Then we just expand our window a little bit. And Y min to Y max, well, we have 220 to 230 already, and it looks like we're right in the middle. So I'm guessing like 225. Maybe we'll try like 223 to 227, something like that. Great. And we still have our intersection in the window. So I'm trying to cut the window down fairly aggressively, but not so aggressively that I have to go back and redo my work. So in this window, I have 85 to 90. This is 86, 87, 88, 89. Looks like 88 is our x coordinate of the solution. And then my y-axis goes from 223 to 227, 223 to 227, 24, 25, 26. Looks like it is right at 225. So what did I say I was thinking? Let me write it up here. I think that x equals 88, or x was what we were calling A. So I think 88 adult tickets and 223, 224, 225 child tickets. So by just zeroing in, we saw that we started from a very large window, and in 5 steps, we think we have the right solution. Is it true that, let's go back to our home screen, is it true that A plus C, or 88 plus 225, equals 313? Yeah, that does work out. And is it true that 12 times 88 plus 5 times 225 gives me 2181? Yeah, that also is true. So that is our solution. Right. So even from a really a very large window, 350 units on each axis, we can zero in on our solution pretty quickly. This is kind of an exponential rate of progress. We're like cutting in half each time. So we get like half as much, then a quarter, then 1/8, 1/16, 1/32, and 32 times 10 is about 350, right? So by cutting it down by something like half-ish each time, maybe getting a little more aggressive when we're more confident, when I see that the solution is way into one side or the other, you know, vertically or horizontally, getting a little more aggressive where I can zoom in pretty quickly. Okay, let's take a look at 2 exercises then. So we have similar exercises to the previous 2 examples we just did. So again, maybe take about 10 minutes or so, work through these 2 exercises, and like usual, in about a minute or so, I'll kind of start jotting down some notes, and we'll come back in about 10 minutes and talk about the answers. And I will, I think, um, get out of the full screen so that I can have the chat up. If you have any questions or thoughts, pop them in the chat and I'll have the chat up. Let me switch my screen share, and yeah, we'll come back in about 10 minutes and work through the answers. Okay, about 2 minutes left. So if you haven't started working on the calculator part, use the systems that I have set up here and try to work through the calculator part in the last couple minutes here. Okay, let's come back together and discuss the solution. So this first exercise, the river cruise boat, very similar setup to our canoe going down the river and back, of course. So I don't think there were too many surprises from the setup of the equation here. This should have looked pretty familiar. There is a little interesting nuance here, right? So we get b equals 24 minus c, b equals 12 plus c is our two equations. We just take, say, b to be y and c to be x, plug those in, we set our window. We're expecting the speeds to be positive. Let's just look at the first quadrant. So from 0 to 10 and 0 to 10, and we graph that. And we actually see that nothing comes up on the graph. So let me get it to graph again. We know that it graphed because it's showing this on the top right here, this like little thinking bar. If you look at the very top right of the screen, I'll do that one more time. Once it does a graph, if it doesn't think you've changed anything, it won't try to regraph it. So you have to go back and trick it and type something else in, type the same thing in again. But when I click graph, look at this top right of the screen on the calculator, and you'll see that there's a little bar there going up and down. That's telling you that it's graphing, but we don't see anything on the screen. This kind of makes sense, right? I mean, one of our equations is y equals 12 plus x. So it's starting at 12 and just getting bigger. We're going to need to expand our screen out a little bit. So using a little bit of critical thinking here, 0 to 10 on both axes isn't going to be right here because we're starting at speed, say 12, and then going up from there, right? If the speed of the current was 0, we'd be saying that the speed of the boat is something like 12 or 24 miles per hour. So let's maybe go from 0 to like 25 and from 0 to 25. This might be too big of a window, but we do see that we get our intersection on there now. This kind of bottom left corner here is what we were graphing before, and we just really didn't see either of the lines in that window. So we had to think, okay, I didn't see either of the lines. What's happening here? Problem solve a little bit, troubleshoot a little bit, realize that, oh, okay, we need to expand our window. And there we go. We've got our intersection. It's to the left and to the top. So maybe it's to the left. So maybe I'll choose like 0 to 10 for x. And it's towards the top. So maybe I'll choose like 15 to 25 for y. Let's see if that does it. Okay, there we go. So what did I say we had? 0 to 10, 15 to 25. Oops, wrong direction. So 0 to 10 for x, 0, 1, 2, 3, 4, 5, I think about 6. So x equals 6, or that corresponds to c equals 6. And in our vertical direction, our axis is 15 to 25. So 15, 16, 17, 18, I think, maybe. That corresponds to b equals 18. This is always a visual thing. It's always a bit of an estimate. So let's check and make sure that 6 and 18 do actually satisfy our equations. Is it true that 24 minus 6 is 18? That is true. Is it true that 12 plus 6 equals 18? That is also true. So these are our speeds, 6 and 18 miles per hour for the current and the boat, respectively. Any questions on that one? So pretty straightforward problem until you get to the graphing on the calculator, where you have to do a little bit of troubleshooting to get the window correct. Okay, this next exercise is a little more complex, although we've seen several like this before. So Julie and her husband own a coffee shop. They experimented mixing a city roast Colombian coffee, which we'll call C, that costs $7.80 per pound, with a French roast Colombian coffee, we'll call that F, that costs $8.10 per pound, to make a 20-pound blend. Their blend should cost them $7.92 per pound. How many pounds of each type of coffee should they buy? So we'll let the variable C represent the number of pounds of city roast that goes into the blend, and F, the number of pounds of French roast in the blend. And should this be is it 20 dash pound? I think it's 20 dash pound. I copy these right from the book usually, so. Okay, so on one hand, I want the total weight, the total number of pounds, to be 20 pounds. So C plus F has to be 20. That's kind of the easy equation to get. But then I have the constraint that I want a certain price per pound for the overall blend. This is where things can get a little bit tricky. We might be, I don't think we'd be tempted to do like 7.80 plus 8.10 equals 7.92. But we might be tempted to do something like 7.8C. That's the dollars per pound for the city roast times the number of pounds for the city roast. That's the cost for the city roast coffee that's going into the blend. That's the cost in dollars for the city roast coffee. And then to that, we want to add $8.10 per pound times the number of pounds of French roast. That's the number of dollars worth of French roast that's going into the blend. We might be tempted to set that equal to like 7.92 and move on with our solution. But note that on the left side, I have in each term dollars per pound times pounds, or just dollars. So this term represents the cost of the city roast coffee that is going into the blend. And this term, the cost of the French roast coffee going into the blend. But if I just set that equal to 7.92, that's dollars per pound. That's the wrong unit. That's kind of like the density of cost of the blend. I need dollars per pound times pounds to make dollars, to make cost. So if I was tempted to write equal 7.92 and move on, I see that my units don't match up. What else do I have floating around that's a number of pounds that relates to the total blend? Well, of course, the 20 total pounds of the blend, I multiply by 20, so that my blend as a whole is 20 pounds, costs $7.92 per pound. My pounds divide out, and I am in units of dollars. So now my units make sense. So if I was, tempted to cut a corner there, checking the units really helps. And I end up with these two equations when I solve for, say, F in terms of C. F equals 20 minus C, and F equals 7.92 times 20 minus 7.8C, all over $8.10. Let's go over to our calculator now. I have f is 20 minus c, or y is 20 minus x. Now I keep in mind I want 20 total pounds, so I could have like 20 pounds of city roast and none of French roast, or 20 pounds of French roast, none of city roast. I probably want to use a window that's a little bigger than 0 to 10 on both axes. Maybe 0 to 20 would be a good window to use. I also expect that I will be able to make such a mixture because if I can select it here, $7.80 per pound and $8.10 per pound are the two things I'm mixing together, and $7.92 is between the two. Kind of like when we wanted to mix two vinegars to make a solution with a certain acidity. As long as that acidity was between the acidities of the vinegars, we should be able to make it work. So I expect to get an answer that's reasonable. I don't expect my answer to be some silly answer like you need -5 pounds of city roast and 25 pounds of French roast. I expect to get a reasonable answer. So I expect it to be a first quadrant answer, but I do see that my intercepts are at 0, 20 and 20, 0. So I'll pick a slightly bigger window. Okay, I need to get my second equation in here. 7.92 times 20. Make sure I put that parentheses in first. Minus 7.8 times the variable x, and the parentheses, that's the numerator, divided by 8.1. All right, 7.92 times 20 minus 7.8 x, all in parentheses, over 8.1. That looks good. In my window, again, like I said, I'm going to go from 0 to 20 on both axes, because that should get my intercepts for the f equals 20 minus c equation, should get my intercepts in the window. And if the other equation intersects, it should intersect in the first quadrant. It should intersect when f and c are both positive. We should be able to get a reasonable answer to this problem. Let me graph. There is my f equals 20 minus c. And oh geez, they have almost the same slope. Right? It does look like there's an intersection, but it's actually really hard to tell where that intersection is, because I'm looking for an intersection of two lines with almost the same slope. There's actually an awful lot that can be said about such types of scenarios, but I have something like this where there is an intersection. It looks like the intersection is a little further to the right than that, but the point is there is an intersection, but the two lines have very close to the same slope. These tend to be harder problems to solve in many different respects, but certainly like looking at this and trying to estimate where do these two lines cross is probably going to be kind of difficult. I could lean on my calculator here, do second calc, look for an intersection. And I get 12,8. Or C is associated with X and F with Y. So this is a prospective solution. But if we didn't want to do that, if I was just looking at the graph, I can see that like, even though the two lines are almost parallel, they're really close to parallel, they're not quite. They do split apart a little bit at the very top left. We can see a couple of pixels at the top left in between them that aren't shaded in. And it looks like at the bottom right, the line, it looks like just a thicker line. It's the two lines are kind of separating a little bit. And we see in the middle, there's a thinner part. I might guess that my solution is in the middle there, kind of to the right half of the screen and the bottom half of the screen. So the right half means I'm looking from 10 to 20 on X, and the bottom half, 0 to 10 on Y. And I still end up with this very difficult to interpret graph, right? So this is where I maybe want to lean a little bit heavier on the calculator's calc menu and look for an intersection that way. Or maybe even uh, just solve for f in terms of c and do like a substitution kind of thing like we would have done a couple of chapters ago when we were talking about applications, right? Maybe I've run out of colors here, so we'll use red. F equals 20 minus c, so 7.8 c plus 8.1 times 20 minus c equals 7.92 times 20. Not the prettiest equation to try to solve, but it is what it is, right? We can make things a little better by making this right-hand side 79.2 times 2, and then we can just bump all the decimals one to the right, and that helps a little bit. Still, again, not the nicest equation to solve, but it is doable, I think. But either way, we should come up with c equals 12 and f equals 8, and then we can check. Of course, 12 plus 8 does equal 20, so we can clearly see that that first equation is satisfied. Let's check the second equation. Is it true that, oops, is it true that 7.8 times c times 12 times 12 plus 8.1 times f times 8. What do I get for that? 158.4. Is it true that that equals 7.92 times 20? And yes. So the second equation is also satisfied. This is a correct solution. Any questions on this one? Okay, let's take a look at this example. This one is very similar to the vinegar example, except here we're dealing with antifreeze. So we had a couple of nice spring days there, but maybe we are worried about antifreeze and coolant and so on again now. Spring came and said hi for just a minute and then had to run. So we have a 40% antifreeze solution and a 70% antifreeze solution. We want to mix them to get a total of 240 liters of a 62% solution. So how many liters of each should we use? So let's call our 40% antifreeze solution, we'll just call that A, and 70% B. Now, on one hand, we want a total of 240. So A plus B, by the way, A and B are the number of liters of each of the antifreezes we want to mix. A plus B equals 240. So antifreeze is often some kind of chemical that's mixed with water or something like that. And that's the percent. That's the percentage of the chemical relative to the whole volume. So if I have A liters of the 40% solution, I have 0.4 A liters of the actual chemical that's in there. And for my 70% solution, if I have B liters of that solution, I have 0.7 B liters of the actual chemical. Isn't it like ethylene glycol or something? There's one of those that's, I think ethylene glycol is antifreeze, and then like propylene glycol is a food additive, and I don't know. I'm no chemist, but they sound a little too similar for me to be comfortable with that. But 0.4A is the amount of, say, chemical in the A liters of 40% solution. 0.7B is the amount of chemical in the B liters of the 70% solution. How much of the chemical is in the overall solution? 0.62 times 240. We have 240 liters at 62% concentration. So that's 0.62 times 240 liters of chemical in the mixture. And again, we've seen similar ones like this before. We've seen, the cooking and cleaning vinegar example before. But instead of solving this by hand, we'll use the calculator to help us with graphing this. So let's say that B equals 240 minus A. Now keep in mind, A plus B is 240, so I'm going to want to use a much bigger window than say, 0 to 10 on both axes. And I'll solve my second equation for B in terms of A as well. So 0.62 times 240, subtract 0.4A from both sides, and then divide that whole thing by 0.7. I have 240 minus in my variable x, and then parentheses 0.62 times 240 minus 0.4 x, and my parentheses, and then divide by 0.7. So does that look right? Looks good. And my window, I'll pick 0 to 240 for both axes. Right, I see my first equation, A plus B equals 240, has intercepts at 0, 240 and 240, 0. And if I'm going to get a solution where A and B are positive, which is the only type of solution that makes sense practically for this problem, then it's got to be in that first quadrant. It's got to be kind of between, in a sense, those two intercepts. Okay. And again, because 62%, the solution I want to make is between 40 and 70%, it does seem like I should get a realistic answer here, and I do. I could keep cutting my window down until I zoom in on this point, but for the sake of time, because we only got 10 minutes left, I'm going to cheat and use the intersect function on the calculator, and we get 64 and 176. So x equals 64, that corresponds to A equals 64, or 64 liters of the 40% solution, and 176 liters of the 70% solution. And that kind of does make sense. 62%, the solution concentration we want, is closer to 70 than 40, and we're using more of the 70% solution than the 40% solution, so that kind of feels right. Okay, so let's take a look at these two exercises. We'll basically use the last 10 minutes or so to work through these, and I will actually just go through and kind of work through them alongside you. And yeah, we'll come back in about 8 minutes or so and wrap up. So I'll just kind of walk through the exercises on paper as you go through them, and then we'll wrap up in the last minute or two, and that'll wrap up our class for today. Okay, so we have about 1 minute left. I just kind of worked through these problems along with you. Um, if you want to, go through them a little more slowly, you can definitely watch the recording. Um, but the first one, we've seen problems similar to this before, so I'm not going to say much about that. The solution was equal parts, 5.5 liters of each. That makes sense because 25% is right between 10 and 40. The second exercise, a little bit different because we were given the total amount of interest, and we had to just be a little bit careful with our units and things here. We also see that our first equation is P equals 65,800 minus F. So we want to actually graph on a window like 0 to 65,800 on both axes. And then we could keep kind of cutting the window down and zooming in if we needed to, but uh, for time's sake, I used the intersection tool and got 57,500 in federal loans and 8,300 in private. So that is our solution for this last exercise.